Welcome to The Explainer. I'm really thrilled to have you here today because we're going on a high-stakes engineering journey into literally one of the most hostile environments imaginable, the vacuum of space. You see, space survival isn't just about massive rockets and heat shields. It's about the invisible, moment-to-moment mechanics of keeping human beings alive in a place where biology dictates they just shouldn't be. Today, we're diving into a fundamental requirement for human life and exactly how we engineer it from scratch while floating in the void. Let's put ourselves right into the boots of an astronaut for a second. Imagine you're orbiting 400 kilometers above Earth. Outside your window, just the black, silent expanse of space. But suddenly, a red alert flashes across your display. Air supply failure. The system responsible for producing the breathable air inside your cabin has just gone offline. Now, you and your crewmates have to work with mission control to identify the problem and fix it. Fast. It sounds like a terrifying scene straight out of a Hollywood sci-fi thriller, right? But for astronauts living on the International Space Station, dealing with the fragile reality of life support systems is a very real, everyday part of their existence. So the ultimate question becomes, when you're completely cut off from Earth's atmosphere, how do you get your next breath? This single question establishes the massive stakes of space travel. Down here, we totally take breathing for granted. But up there, it requires constant, active intervention. For over 25 years now, the air supplies systems on the ISS have absolutely revolutionized space missions, pushing the boundaries of what's possible. But getting to where we are today and figuring out how to go even further into deep space, well, that required decades of incredible evolution in engineering. Okay, let's dive into this with Section 1, the Apollo Oxygen Method. 0.8. Now, this is the crucial baseline for everything we're about to discuss today. Creating a breathable environment means supplying oxygen and scrubbing out exhaled carbon dioxide. And every single astronaut in space requires, on average, exactly 0.8 kilograms of oxygen every single day just to survive. Obviously, if you have a crew of 3 or 7, that number scales up pretty quickly. So how did the early missions actually meet this rigid, non-negotiable biological demand? To really appreciate the marvels of modern space station engineering, we first have to travel back to the earliest era of space exploration, back when missions were short sprints rather than long-duration marathons. Think about the Apollo 11 mission to the moon. It was an 8-day trip with 3 astronauts. They easily met that 0.8 kilogram daily requirement by just packing about 50 kilograms of oxygen into pressurized tanks. It was heavy, sure, but totally manageable for a short trip. But then, compare that to the International Space Station. A typical 6 to 8 month expedition with 7 crew members requires over 1,000 kilograms of oxygen. You'd literally need to ship about 30 large heavy tanks into orbit. Constantly blasting that massive payload of metal and compressed gas up gravity's steep well, it's astronomically expensive and incredibly inefficient. Which brings us to Section 2, making air from water. Because shipping those massive tanks was no longer viable, engineers had to figure out how to manufacture oxygen on board. And to make air, you first need water. Thankfully, the ISS has a spectacularly robust recovery system. The station captures nearly every single drop of moisture on board. We are talking about capturing the sweat off the astronauts' brows, the moisture from their exhalations, leftover wash water, and yes, even their urine. Every single drop is reclaimed and heavily purified into fresh, highly potable water. And once you have clean water, you've got the raw material for air. Here's the elegant chemistry that actually keeps our astronauts alive. The clean water is routed into a device called an electrolyzer. It's essentially a system equipped with 2 electrodes, one positive and one negative. When a powerful electric current is applied to the water, it physically breaks the H2O molecules apart, forcing them to separate into oxygen gas and hydrogen gas. The life-giving oxygen collects near the positive electrode, while hydrogen bubbles form near the negative one. It's a beautiful, simple chemical reaction. But doing this in space introduces a massive complication. Now, what's really interesting is Section 3, the zero-gravity bubble problem. Doing this chemistry in space introduces a hidden hurdle you probably wouldn't ever think about on Earth. In orbit, where everything is in freefall, bubbles tend to cling. On Earth, if you boil water or run an electric current through it, gravity holds the heavier water down and buoyancy forces the lighter gas bubbles to naturally float right to the top. It sorts itself out. But in the microgravity of space, there is no up for the bubbles to float to. Without gravity to separate the gas from the liquid, the hydrogen and oxygen bubbles just stubbornly stick to the electrodes. And if you can't get the gases out of the water, the whole system chokes and stops working. So how did engineers actually solve this? Well, with brute force physics. Currently, on the ISS, water is pumped aggressively through the electrolyzer, essentially sweeping those clinging bubbles away into a separate machine called a separator. Think of it exactly like the final spin cycle of a washing machine. The separator spins the gas-filled water rapidly. The centrifugal force throws the heavier liquid outward to the edges, leaving the lighter gas to safely collect in the center where it can be harvested.
Once separated, these gases have very specific destinations in a complete, self-sustaining loop. The oxygen is, of course, released directly into the cabin to keep the crew breathing. The hydrogen gas is a bit trickier. It can simply be vented out into the vacuum of space. Or, in a stroke of absolute efficiency, it can be routed to a reactor, mixed with the carbon dioxide the astronauts exhale, and turned into methane and even more water to feed right back into the system. It's an incredibly clever way of repurposing waste. But here's the stark reality. This spinning separator works for the ISS right now, but it's definitely not perfect. That centrifuge relies on a lot of complex, rapidly moving parts. And as any engineer will tell you, moving parts eventually break or malfunction. They require constant maintenance, spare parts, and precious astronaut time to fix. If a pump breaks while you're just 400 kilometers above Earth, you can always wait for a resupply ship. But if a pump breaks when you're millions of miles away on a mission to Mars, that's a terrifying and highly dangerous liability. Which naturally leads us to Section 4, Magnets for Deep Space. As space agencies prepare for year-long trips to Mars, we absolutely need a system that ditches the moving parts. To understand how we do that, we need a super quick physics lesson on the Lorentz force. This is a fundamental property of how electrons and magnets interact. When negatively charged molecules move perpendicularly through a magnetic field, that field exerts a force on them, the Lorentz force. It literally pushes the molecules sideways at a perfect right angle to both the electric and magnetic fields. This invisible mechanic is the key to the next big innovation in space survival. Right now, engineers are researching a revolutionary system called MOGA, which stands for Magnet Hydrodynamic Oxygen Generation Assembly. I know, it sounds like something directly out of science fiction, but the science is very real. Instead of using a mechanical pump to spin the water and separate the gases, MOGA uses carefully positioned magnets. By applying the Lorentz force we just talked about, the magnetic fields themselves swirl the liquid. The invisible hand of magnetism physically separates the oxygen and hydrogen gases right there inside the electrolyzer. The advantages of MOGA are absolutely game-changing. Because the liquid is spun by magnetic fields rather than a physical centrifuge, there are zero moving parts, no spinning gears, no mechanical pumps to break down. This means exponentially less maintenance and less need for heavy replacement hardware. It shrinks the size of the life support system, frees up critical onboard space, and most importantly, it gives astronauts their time back so they can focus on science rather than fixing plumbing. This level of reliability makes MOGA the ideal candidate for deep space travel, especially those year-long journeys to Mars where a resupply from Earth is simply impossible. MOGA is still in the research phase, sure, but it perfectly represents the incredible ingenuity required to step out into the cosmos. With a more robust oxygen system, future explorers will quite literally be able to breathe a little easier. And it leaves us with this final thrilling question. As we successfully engineer the very air we breathe for Mars, effectively mastering our own biology in the void, what other Earthbound limitations will we leave behind? The solutions we invent to survive out there will undoubtedly reshape what we believe is possible everywhere. Thank you so much for joining me to explore this fascinating slice of space engineering on this